Okay, so this is our first video on what we call modern physics. When we say modern, we don't mean modern in the sense that you or I might usually use the word. Modern to you guys might be something the last 10, 20, 30 years. Modern physics really relates to the time period from 1900 on. From that time period, we got a lot more technologically sophisticated. We had a lot better capability of our equipment, our machines, and we were able to study things that we weren't able to study before, and we got a lot of really interesting results out of this. And as the lead-in to modern physics, this is why I lead in with waves. Because this whole story kind of starts with waves and light, really, and how light didn't really fit into a category of either being waves or particles. Anyways, we start with waves. And we have talked in the waves unit about some properties that waves have that are very unique. Some of these properties include constructive and destructive interference. I'll just give you two quick examples of that. You should remember this. Constructive interference, let's say we have two wave pulses coming towards one another. When they combine, we know that they will be twice as tall. I know my picture is terrible there, but you know that waves will add if their orientations are the same, if their amplitudes are both positive, for instance. On the other hand, destructive interference. Let's say we have two square pulses, like this, moving towards one another. When they go completely over the top of each other, they will cancel each other out. That is destructive interference. Okay? We've already talked at length about this, and you guys have gotten pretty good at constructive and destructive interference. Now, on the other hand, diffraction is another property. Diffraction has to do with the bending of light rays, or any wave, when it goes through an opening in a barrier. So what I'm going to draw are some wave fronts. The wave fronts are coming in towards an opening in a barrier. Notice the wave fronts are all lined up here. They're nice plane waves is what we would call them. Plane is in, not like plain boring, plane is in like a flat surface. But once they get through the opening, they have this tendency to spread out like this. That is diffraction. Waves spreading out once it gets through an opening in a barrier and spreading out into the area behind that. So if you combine these two effects, interference and diffraction, you can get some really neat effects. Now, there was a conversation all the way back from like Isaac Newton's time. He even took a stance on this, on the nature of light. Light's very clearly different from ordinary matter. Okay? It doesn't act like ordinary matter. People were not sure whether light was a particle or whether it was a wave. And so people devised experiments in order to try to determine whether it's a particle or whether it's a wave. And one of the first experiments that seemed to really show what it was known as the double slit experiment. Double slit experiment. Now, here's what the double slit experiment is. Okay? This is a pretty good picture of it. While you're looking at this picture, let me summarize for you. You have a light source, you have a barrier, you have two openings in said barrier, and you have a screen back here for the light to shine through the barrier onto. Now, let me use an analogy. Okay, let's consider this. People, again, we're not sure whether light was made up of particles, little tiny light particles, or whether it was a wave. And if light was particles, it was theorized. And to help you visualize this, consider if you play tennis, there's a tennis. You can get a tennis ball launcher to launch tennis balls at you, and you hit them back. Imagine you have a tennis ball launcher, I almost think like a tennis ball machine gun, and you can shoot lots of tennis balls through this. Let's imagine this experiment done with a tennis ball gun. Okay. So if the light is replaced by a tennis ball gun, you have two very narrow openings in this barrier that's in front of you. If the tennis ball hits the barrier, not around an opening, it will just bounce back. If it goes through the opening, it will continue onto the screen. Let's say the screen is Velcro. You'll see the tennis ball stick to the Velcro. Well, kind of the obvious thing for you to expect is that you will only get, let's say on the screen, even though the screen is entirely Velcro, you would probably expect to only see tennis balls directly behind and in line with the gun on the screen. You only see like two little strips of tennis balls, okay? Maybe a little bit bigger than these slits, But still, you would only expect to see tennis balls in certain places. You wouldn't expect to see tennis balls in the very middle. That would imply that tennis ball went through the slit and then somehow just magically changed direction and went to the middle. You would only expect to see tennis ball pattern here. So, it was theorized that if light was made of particles, if you took a light source and you had a double slit here, that you wouldn't get light all over the screen. You would get light in only 2 places. That's what was theorized. And what it turned out actually happened, as you can see from the picture. We have a light source, we have 2 slits. Count how many bright spots there are. We call them fringes. I have 1, 2, 3, 4, 5, 6. 6 fringes, okay? That is strange, to say the least. It's very, very strange. Now, with these 6 fringes, that's showing us that light does something kind of interesting. And I want to show you what is actually happening here. So I'm going to go to a little interactive that I have. This is the same sort of idea. We have a barrier with 2 slits in it, here and here. We have a screen that the light is being projected onto. We'll also have a little graph of intensity here. And we have a laser light, okay? This is a light generator. When I click on this, you'll see light start to be generated. So I click on it, you see light pulses coming through. Now, watch what happens when they get through the slit. That's your diffraction, okay? Light is diffracting as it goes through this barrier and starts to spread out. And then watch what happens when the light that spreads out starts to overlap. Maybe you can't see it that well, but we're starting to get some interference. We have light waves kind of running into one another, okay? Now, I know you probably can't see that well, but watch what happens on the screen if you can, and watch what happens right here on this graph. This graph is just showing the brightness of the screen, essentially. So if you see a peak, that means it's very bright there, okay? So watch as that starts to build up. This is the same sort of idea here. And you can see we've got this kind of wavy pattern. And what I'm getting is I'm getting some bright spots here, here. Let me turn off the lights. See if you can see it any better. I'm getting some bright spots on the screen. Here, 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 here. Probably like 8 or 9 of them, okay? And again, the reason I'm getting those bright spots is because the light, even though it's coming in as plane waves, is diffracting around this barrier, or once it gets through the barrier, and then the light is interfering with itself. Instead of just 2 bright spots, I'm getting 9. If light was made of particles, it's theorized, light would not do this. Okay? Particles don't interfere and diffract with each other. Particles don't spread out as they go around a barrier. That's just not how they work. Okay? They don't interfere with each other either. It was theorized based on this, that light must be made out of waves. Waves must be the composition of light. It must be a wave-based phenomenon. Scientists reason that if light were made of particles, it could never do this. It would only show up as 2 bright fringes. So this seemed to settle it. This experiment was done in about 1870 something. This seemed to settle it. Light, definitely a wave. However, there was another phenomenon. We kept studying light, because we still didn't know everything about it. Okay? In the 1900s, there was a new experiment done. This experiment was known as the examination of the photoelectric effect. Photoelectric effect. And the reason behind it, it's actually a very clever experiment. So, it has to do with how energy is transmitted in a wave. Now, normally, in most waves, the energy is related to the amplitude. And for a light wave, amplitude is given by brightness. So brighter light means a higher amplitude for that wave. Okay? So scientists originally thought that the brightness of a light wave was proportional to the energy. Okay? If you increase the brightness, they've reasoned, you can increase the energy of that wave. So they figured one way that they could create a current. Okay, remember, they're just invented methods of conveying current, within the last 50 or so years. One way to create a current should be to take a really bright light and shine it on a piece of metal. Okay? And metal, as we know, has many free electrons that aren't quite free, but are not very tightly held. We could take a bright light, shine it on a piece of metal, And what this will do is that energy from the wave, from the light, should allow those electrons to ionize. It should allow them to leave their parent atoms. And then if those electrons, those newly free electrons, could be directed a certain way, now you've created a current. So they figured one way they could create a current, shine a really bright light on a piece of metal, ionize some electrons, and push them in a certain direction. That'll create a current. If you have a brighter light, that should increase the current. And it should not only increase the current, it should make the electrons more energetic. Okay? It should give them more energy. And the type of energy an electron can have kinetic energy. So if you give them more energy, they will move faster. It was reasoned. And that is a really clever idea. Okay? Shine light, make a current flow. Sounds good to me. Okay? Now, they actually tried this, and I will show you what they actually did. With a little help here. Okay? This is a light. It is shining, or it will be shining, on a piece of metal. And the piece of metal will emit electrons. The electrons will move this way, and then they will go into the wires, and they will create a current here if electrons are actually emitted. And let's see, I can change the intensity of my light, make it bright or not. I can change the wavelength as well. I'm going to start with the highest wavelength, infrared. So it was reasoned that if you just make a bright enough light, you will get charges to flow. You'll free some electrons. And there is a current reader down here. Sometimes it seems like it's a little broken. Not right now, but when I've used this before, it seems like it's not quite right. Your job is to look to see if electrons are coming out of here. So as I increase the intensity, it's reasoned that the current should increase. But if you notice, I just increased the intensity to 100%. Very, very bright light, very, very bright infrared light. I get no current. I don't see any electrons coming out. Well, that's kind of funny. Maybe let's try a different wavelength. Let's try somewhere in the reds. Nothing. Okay? We'll try yellow, or greeny yellow. Still nothing. Okay? Seems like the frequency is not really doing anything. Well, let's keep going. We haven't tried green, blue, purple, UV. Let's try green. Right about there. As I increase the intensity, okay, I'm starting to get, I got something. I got an electron coming out, I got another one, okay? And you can notice that they're all moving pretty slow. If I increase the intensity more, sometimes it takes a while for this simulation to start for some reason. If I increase the intensity more, I seem like I'm just getting more and more electrons, okay? You can see that the number right now is a lot. If I decrease the intensity, I don't get quite as many, okay? And this doesn't quite gel with the theory that people had. The theory people had was that the more intense the light, you'll get a bigger current and you'll also get more energetic electrons. All of these are about the same amount of energy. Let's try something. We only got a current when we got over far enough in the wavelength for some reason. Let's try decreasing, I should say, the wavelength. And just so you remember, decreasing the wavelength is the same as increasing the frequency since they are inversely related. Let's see what happens if I decrease this even more. You see that I'm starting to get some electrons that are moving a little bit faster? I got some faster ones here. They're passing the other ones. So they must be more energetic. Okay? Matter of fact, if I keep going to the left and keep decreasing this, you'll notice that I still get a couple slow ones, but I'm getting faster and faster electrons, and now I'm into the ultraviolet range. If I go all the way up, I'm getting some really fast electrons. I'm getting a pretty big current. The current is very high here. It doesn't look like quite as many electrons, but that's only because they're really flying. If I turn down the intensity at this point, it's not going to cause them to be any less energetic. It's just decreasing the amount of electrons that are flowing. So to summarize, the current seems to be related. The current has two things that affect it. I'm not going to get a current if I don't have a small enough wavelength, or a high enough frequency if you want. And the intensity can change the amount of the current, but it doesn't change the speed that the electrons are flowing at. On the other hand, the speed seems to be proportional to the frequency. I'm going to stop there, and I'm going to go to a different video. But that is a really interesting thing that happens, and it's completely against what we would have expected. So when I come back, I will tell you
a little bit about what we did expect to happen, or what this means, I should say.